Okay, hello class. Today we're going to study chapter 13, new chapter. It's called States of Matter, Liquids and Solids, and then eventually we'll study changes of state. Keep in mind that we already studied the first part of this chapter, 13.1, which was on gases. We studied that along with chapter 14, which was the gas laws. So for chapter 13, we're simply going to talk about liquids and solids, and then we're going to talk about phase changes or changes of state. So here are our lesson objectives over the next 2 to 3 class periods, depending on how far we get. So section 13.2 in your textbook talks about liquids, and so we're going to really talk about how the atoms are arranged and some basic properties. And then chapter 13.3 talks about solids. We're going to talk about how the atoms are arranged and then basic properties of solids. And then finally, we'll move on to changes of state, which is the more difficult part of this chapter, 13.4. Talk a little bit about equilibrium, what that means. Then Le Chatelier's principle is discussed here, but we're going to talk more about that in another unit. And then we'll move on to the 6 basic phase changes. And then finally, we'll talk about being able to describe parts of a heating and cooling curve and understanding a phase diagram. And what I want to point out is that these last two will be some calculations involved, and these are definitely more difficult, being able to describe the parts of a heating and cooling curve and then understanding a phase diagram. I might try to put together some separate lessons where I work some problems with those. So let's first identify the 4 states of matter. Let's see if you can do that on your own right now. Think of what they are in your head, and then go ahead and see if you can jot those down in your notes. I'll give you about 20 seconds. 4 states of matter, and then we'll show them briefly. Three of them are pretty straightforward. Three of them are pretty straightforward. The 4th one is a little bit more difficult, and of course there's actually now a 5th one, which we'll have a couple slides on as well. Okay, so first state of matter, of course, is a solid. This is some solid sulfur. Another, of course, is a liquid, and water would be a classic state of matter for liquid. And then, of course, gas, any type of gaseous substance like oxygen or nitrogen or carbon dioxide is another state of matter. And, of course, actually, plasma is the 4th state of matter that we know about. It's an ionized form of gas. Turns out that about 99.9% of the known universe is made up of plasma. So on Earth we live in a place where actually we are very familiar with solid, gas, and liquid, but most of the universe would be more familiar with plasma. That makes up 99.9%, I believe, of the known, in fact it might even be more than that, of the known states of matter in which substances are in. So most elements are actually in the form of plasma, mostly of course in stars and things like that. Now we did have a video that I showed. Not all of you saw it. For instance, I know 4th period didn't see it, but some of the other periods did, and some of you didn't see all of it. But in that video, the NOVA video on absolute zero, there was the discussion of the fifth phase of matter, which is a Bose-Einstein condensate, or a BEC. To the left here is a picture showing the Bose-Einstein condensate. Here is the actual pure Bose-Einstein condensate, and it's showing it as it progresses. It's a state of matter of a dilute gas of bosons cooled to temperatures very near absolute zero. This state of matter was first predicted generally in papers by Satyendra Nath Bose and Albert Einstein in 1924 and 1925. Okay, so this is an actual picture of, I think, actually the first Bose-Einstein condensate formed. Now, don't worry, if I ask a question on a test or a quiz, about a BEC. It's going to be a very simple question. This isn't something that you necessarily have to take detailed notes on. This is more for just kind of basic science, learning more about science and learning about some neat stuff that's going on right now. Okay. So the next slide I have a little bit of a timeline of the Bose-Einstein condensate, the fifth phase of matter. And in 1925, Einstein extended Bose's work and proved mathematically that you could cool these bosons to very low temperatures, and you could actually cause them to fall into a quantum state, which he said would be a new form of matter. In 1938, Franz London successfully showed that BECs, this Bose-Einstein condensate, is probably what's happening when a liquid like helium becomes superfluidic and superconductivity. Again, both of these properties were superfluidity and superconductivity. They showed examples in the NOVA video as well of that, so if you're curious about that, go back and look. That was where the liquid helium actually went through the glass when it became superfluid. Now in 1995, the first BEC was produced by Eric Cornell and Carl Wyman at the University of Colorado at Boulder. They used rubidium atoms. They cooled them to really cold, 170 nanokelvin. And also another guy, Wolfgang Ketterle, also made a BEC just shortly after them. And all three of these gentlemen got the 2001 Nobel Prize in Physics for basically producing the first wave of Bose-Einstein condensates. In 2010, the first photon BEC was observed. And just as recently as this past December, right before break, I think the paper came out right around the day we had our final, hydroxyl groups, those are OH minuses, we call them hydroxides here in class, were cooled to near zero. They did not make a BEC, but they think that they probably will. And that'll open the door to possible BECs that are anions, which they think will have lots of interesting properties. So this is the video. There's a little snippet from the NOVA special. It's about 3 minutes and 40 seconds, but I thought I would just show it again because one of the Ketterle's people that works with him at MIT actually talks a little bit about what these BECs are. So not everybody saw this, so we'll go ahead and play it.
In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can also be particles and waves at the same time. Even for great minds like Albert Einstein, this strange paradox was hard to accept. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he'd been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid or liquid or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate, which has never been seen in nature.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. they undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or that. There and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
So there you have it, a little bit about what a Bose-Einstein condensate is. Again, I would strongly urge you to go to the NOVA Absolute Zero, watch the entire video if you haven't seen it, where it talks about the discovery of BECs and sort of current state of research. So what are the factors which determine which state of matter you are in? So let's just show quickly, there's really three things that sort of determine what state of matter you'll be in. The first will be particle arrangement, so the arrangement of the particles. Gas, solid, liquid, you saw with the Bose-Einstein condensate, they have sort of a weird arrangement that's hard to understand. Next one would be the energy of the particles, how fast they're moving in a way that's related to the temperature of the particles. So how the particles are arranged, their energy, and finally the distance between the particles. So those three factors really determine what state of matter you are in. Okay, so again, particle arrangement, energy of the particles, and the distance between particles determine which state of matter you are in. So let's first talk about solids. The state of matter is solid, so the particles here tend to be tightly packed and they vibrate about a fixed position. So if we look here, this little diagram, this bouncing ball, if you look really closely inside the circle, you see that actually solids, even though they're tightly packed, they do move. They move around a fixed position, vibrating, sometimes rotating slightly. They're all connected in this lattice, is what we call it, but they tend to again, still move quite a bit and move fairly fast. So again, we tend to call this a lattice structure when we talk about solids, L-A-T-T-I-C-E. And again, particles of solids are tightly packed, vibrating about a fixed position. And what happens is solids have a definite shape and a definite volume. So they always have a definite shape and a definite volume. Okay, so take those notes down. Probably the most important thing is that solids have a definite shape and a definite volume. So the next state of matter we'll talk about is liquid, and particles of liquids are tightly packed but are far enough apart to slide over one another. And so if you look here, you see that they're still moving about in this diagram. In this video, the link isn't very good, but if you look at this on the regular PowerPoint on the website, you'll see that they move pretty good. Well, now it looks like it's moving pretty well. So they kind of move by each other. I kind of like to use my analogy that a solid is sort of like Marines in formation, and a liquid is sort of like people on a sidewalk in New York City, and a gas is like, I don't know, a few people in Alaska going around on snowmobiles, and there's just a few people there. That's sort of my analogy of the difference between gases. The solid would be the Marines, the liquid would be a large city, people flowing by each other, and I like my people in Alaska on snowmobiles, say, leaving a meeting and then they all take off in different directions. That would be sort of like a gas. Now, liquids have an indefinite shape and a definite volume. So again, liquids have an indefinite shape and a definite volume. So their volume is always the same, but depending on what you pour them into, they take the shape of the container. Okay. So take those notes again. Liquids have an indefinite shape and a definite volume. So 500 mils of water will always be 500 milliliters of water, but its shape will change depending on, obviously, where you throw it. You all pretty much have experienced that. Okay, I'll give you a few more seconds to get those notes down. And this last bullet point, this indefinite and definite, are the types of questions they'll ask you. You know, they'll say a solid, which of the following isn't true, solid has an indefinite or definite shape. These are the types of things that they ask you a lot of times. Now, the last one, even though we're not studying it this chapter too much, is still I'm going to briefly talk about gas. States of matter, gas, or particles of gases that are very far apart and move freely. Okay, these particles are very far apart and move freely. They tend to move pretty quickly. And of course, gases have an indefinite shape and an indefinite volume. Their volume can change because as long as they can go outside a container. If they're in an open space, their volume will change. If they're in a container, their volume will be the size of the container if the container's closed. But if the container's open, their volume will change. So we say they have an indefinite shape and an indefinite volume. So the next thing I want to talk about really quickly is the compressibility or the compression of gases, liquids, and solids. This is one property of gases, liquids, and solids. I'll just put up this little, where I'll go through this. Gases are compressible fluids. Their molecules are widely separated, so actually you can take gases and compress them quite a bit. Liquids are actually, believe it or not, relatively incompressible fluids. Their molecules are more tightly packed, you'd think, but as soon as you put them in a system and you add a piston, they don't really compress that much. So they are actually pretty tightly packed. And then solids are pretty much almost incompressible and rigid. Their molecules or ions are in close contact, so they don't move. So again, the take-home message here would be that, you know, gases are compressible, and for the most part, liquids and solids are non-compressible. So really, liquids and solids are actually very similar in this respect compared to gases. Okay. So again, gases are compressible, liquids are non-compressible, and solids are non-compressible. And here's just a little diagram to sort of show that the difference between a gas, liquid, and solid. I think this picture does a nice job of sort of showing you why it's easy to compress the gas. If you try to compress the liquid, put a circular piston into there, you can see it's not going to compress very much. A little, but not a lot. And that a solid will then actually hardly compress at all. Okay? So again, gas is widely separated. Liquids and solids, their molecules, or the atoms, are pretty close together. Okay, so the next, I think there's 2 slides left. One's property of liquids and one's property of solids. So let's just quickly talk about the property of liquids. Okay. So liquids have a relative high density. So hopefully this comes up. Yeah, relatively high density, and we just talked about their relative incompressibility. We just talked about that, so they don't compress very easily. They do have an ability to diffuse, so they can spread out and diffuse through different things. Talked a little bit, obviously we know gases can do that as well. They also have something called surface tension, which leads to things like these water bugs, if it'll pop up. My connection's really slow. There they are. So surface tension. And there's the water bug. So it uses surface tension of the liquid to stay on top. And surface tension is somewhat related to viscosity, which is sort of the thickness of a liquid. The next thing that liquids do is, we know in plants they have something called capillary action, which means their ability to move upwards against gravity. Classic example of this is if you take a celery stalk and put it in some colored water, you can eventually have the leaves turn red. A lot of you might have done that type of an experiment in middle school or something like that. I think I do have a picture of that. It's just taking a long time to load up here. And then the next thing, so again, here's the picture of the celery up there in the upper right hand corner. This is a pretty classic experiment you might do in a bio class or something. And then the other thing with liquids is we're going to spend a lot of time coming up talking about vaporization. Vaporization is 2 processes. It's evaporation and boiling. Boiling is where you add heat and obviously you make it go away. Evaporation is more of a passive process where it basically goes slowly over time. But they're both vaporization, which means the liquid is turning into a gas and going away. But liquids have various properties of that depending on the liquid itself. And then the last one I think here is freezing. So liquids can also turn into solids and freeze, okay? And so they have different freezing points. So again, those are the properties of the liquids I want you to have kind of a general understanding of as you go through your reading. They're high density, meaning they're still pretty closely packed, which makes them not easy to compress, but they do diffuse. They have surface tension, viscosity, capillary action, again, which is the ability to move upwards against gravity in roots and things like that, or I guess the stoma, and then vaporization and freezing. Okay, I'll give you like 10 seconds or so to finish writing those down. The real big one that we'll do a lot with is talking about vaporization, the evaporation and boiling process. So the 2 again that we're going to spend a lot of time talking about are these 2. We're actually going to end up assigning values to these and numbers, and we're going to talk about how we actually can calculate the energy involved in vaporization or freezing. So let's talk about the properties of solids. And so the first property is obviously they're very dense. We know that. It's probably something you learned even in elementary school, that solids have relatively high density. You just learned that solids are pretty hard to compress, so they have what's called a high incompressibility. Solids also have a very definite melting point. So most solids will have a melting point where they melt at a very specific degrees Celsius. So something says, oh, it melts at 10 degrees Celsius. It will melt exactly at 10 degrees Celsius. So solids have a definite melting point. Most solids don't diffuse. In other words, particles of the solid don't leave or move throughout the air and become sort of part of the air. There are a few. Sulfur is one where if you have a piece of sulfur sitting around, the sulfur will end up, you'll kind of smell that smell around it, so it's diffusing into the atmosphere. Some people might say stinky cheese diffuses. However, cheese technically isn't a solid. It's a different kind of solid called a colloid, which we'll learn more about later on. Probably one of the big different properties of solids is that they sort of have two different forms. One's called what's known as an amorphous form, and another is called the crystalline form. And the reason we bring this up is because the difference between amorphous and crystalline is really can be a very big difference in what the solid looks like. Okay, so that word is amorphous. Sort of means without order or without shape. I forget exactly the meaning. Crystalline is highly ordered. So one way to think about this is amorphous means not ordered, and crystalline means highly ordered. Okay, so again, amorphous means not ordered, and crystalline means highly ordered. Now here's a great example of the difference between amorphous and crystalline. On the left-hand side, you have a chemical which has the chemical formula SiO2, and that could be something known as quartz. If you look at quartz under a microscope, it's a very pretty rock. It's very ordered, and it has this very kind of star-shaped pattern to the sulfurs. To the silicons, and the oxides are in a very predictable, ordered pattern. On the other side is amorphous SiO2 is actually glass. Both of these are actually sand, beach sand, but you can see the difference between glass and quartz at the molecular level, and obviously you guys are probably pretty familiar with the differences in these two substances at the macroscopic level. When you look at them, when you look at glass and quartz, you might not necessarily predict that they come from the same substance, or they're really the same chemical. So that's something to think about. Okay, so let's talk about homework. So there's two homeworks that will be handed out today, homework number 60 and homework number 61. Homework number 60 is a 13.2 section review worksheet. So these are these worksheets sort of where you go through and fill in the blanks and do the matching and stuff from the book as you do the reading. And then 13.3, a section review as well. So one is on liquids and one is on solids. The due dates for these will be posted on the calendar on the website. They should already be posted. So anyways, I hope that all is going well. I hope that you all had a really nice break. And see you soon. Have a nice day.